Okay, so I found this applet on the internet. I'm gonna provide you with the web link on the description of this video. It's actually showing you the relationship of an exponential function and its derivative. For this particular case, the exponential function appears right here and is 2 to the x, and it's graphed in blue. So I can move along this line, and for every point on the curve I have the tangent line, and the slope is the number that is after f prime of that particular x value. So I can see the f at that x value right here, and also I can see the derivative or the slope of the tangent line at that point. If you can take a look, when I divide the derivative by the value of the function, these two numbers always change, but the ratio remains constant. So this is exactly what it means when we're taking the derivative of an exponential function. You will see that the derivative of an exponential function is proportional to the function. So for example, for 2 to the x, everywhere I move, this ratio right here never changes. But this number, this ratio, is unique to the base 2. If I change the base to 3, then the ratio, although it remains the same for no matter what x you have, is going to be different. For base 3 is going to be 1.09. So what happens when I have e to the x instead of that? You notice how no matter for what x, the ratio between the derivative and the function is always 1. So that's what it means to take the derivative of e to the x is exactly e to the x. So e to the x over e to the x is always 1. And not only that, but at 0, well, it is also 1 as well. And so that's what is showing in this graph, and that's why the number A is very special. Okay, so the algebraic justification for it appears in slide 11, and in slide 12 the conclusion is shown. The derivative of a function is proportional to the function itself. Just because the derivative of 0, this will be some number, and for f of x equals 3e to the x, that derivative is worth 1. So that's why f prime of x is 1 times e to the x, which is just simply e to the x. Applied to the examples, I'm gonna use that rule. So when I'm trying to take the derivative, I know that the derivative of a difference is just the difference of the derivatives. So f prime of x would be the derivative of e to the x, which is itself, minus the derivative of x, which is simply 1. And then f double prime of x, I take the derivative of e to the x again, and I get e to the x. And the derivative of 1, since it's a constant, that will be 0. So the second derivative is just simply e to the x. Graphically, what it means is that I'm going to have my function. This is f. So the graph of f is right here in purple, and then the graph of f prime is there as well. And the only thing you have to remember is that when the slope is 0, then the graph of the derivative will cross the x-axis, and then this function is decreasing on this side. That is why f prime is negative, and then f is increasing on this other side, and that's why f prime is positive. When I say f prime is positive, I mean f prime has y coordinates that are bigger than 0. On this area, on this section, f prime has y coordinates that are less than 0, negative. And f double prime will just be e to the x, and it's showing the same thing. I think I mentioned it to a few people. When I'm taking the derivative of polynomials and I take higher derivatives, ultimately those derivatives are going to be 0. But it's not the case for exponential functions. If I keep taking the derivative of this function over and over again, I'm going to get e to the x, e to the x, e to the x, and that will never be a constant or 0. In this problem, I'm trying to find a point on the curve y equals e to the x such that the tangent line is parallel to the line y equals to x. It may sound like a lot of things going on in here, but if I have a line parallel to another one, the only thing that means is that the slopes are the same. So that's an important piece of information. So I'm expecting the tangent line to have a slope of 2. Therefore, the derivative should be 2. So they are asking me, when is the derivative actually 2? So I'm going to take the derivative of y, which is y prime equals e to the x, and that has to be 2. So e to the x, when is it 2? When I solve that equation, remember I'm going to apply natural log on both sides. So these two cancel out and I have x equals natural log of 2. Now I found the x coordinate of the point that I'm looking for. Now how do I find the y? By replacing in my equation. Y equals e to the x. X is natural log of 2. And you know by inverses these two cancel out, so I have y equals 2. So the point natural log of 2 has a tangent line that is parallel to the line y equals to x.